Welcome. Today we will see chapter number 3, pressure vessels. These are some images of the pressure vessels. Now you may be thinking that what is meant by pressure vessels. Now we are knowing that pressure vessels are used to store the fluid or to store the liquid or gases under pressure inside the vessel. We have seen on road many vehicles that are containing petroleum products, milk, water tankers are traveling here and there. Therefore, that type of vessels are known as pressure vessels. Now we will see definition. Same, vessels, tanks and pipelines that carry, store or receive fluids are called pressure vessels. A pressure vessel is defined as a container with a pressure differential between inside and outside. The inside pressure is usually higher than the outside, except for some isolated situations. Now we will see different components of pressure vessel. First is inlet nozzle, head, this is known as shell, catalyst bed, support grid, lower catalyst bed, outlet collector, outlet nozzle, this is the skirt support and this is the base. The fluid inside the vessel may undergo change in state as in the case of steam boilers or may combine with other reagents as in the case of the chemical reactor. Pressure vessels often have a combination of high pressures together with high temperatures and in some cases flammable fluids or highly radioactive materials. Because of such hazards, it is imperative that the design be such that no leakage can occur. In addition to these vessels, have to be designed carefully to cope with the operating temperature and pressure. It should be borne in mind that the rupture of a pressure vessel has a potential to cause extensive physical injury and property damage. Plant safety and integrity are of fundamental concern in pressure vessel design. Now we will see applications of pressure vessel. Pressure vessels are used in industrial compressed air receivers, domestic hot water storage tanks, diving cylinders as in scuba diving, recompression chambers, distillation towers, autoclaves in medical industries to sterilize, oil refineries and petrochemical plants, nuclear reactor vessels, pneumatic and hydraulic reservoirs, storage vessels for liquefied gases such as ammonia, chlorine, propane, butane and LPG. Now we will see different materials used in the construction of pressure vessels. First is steels, non-ferrous metals such as aluminum and copper. Next is titanium and zirconium. Non-metallic materials also used for construction of pressure vessels such as plastic, composites and concrete, and metallic and non-metallic protective coatings. There are various materials used in the construction of pressure vessels and their characteristics are as discussed above. First is carbon steel, strength and moderate corrosion resistance, low alloy steels, strength at high temperatures, stainless steels, corrosion resistance, nickel alloys, corrosion resistance, copper alloys, seawater resistance, aluminum, light, low temperature toughness, titanium, seawater, chemical resistance, refractories, very high temperatures, non-metallic, corrosion and chemicals. Now we will see factors affecting the selection of material for the pressure vessels. First is process fluids, second is operating temperature, operating pressure, fluid velocity, contamination of product, required life of the equipment, cost of the materials of construction. Now we will see classification of pressure vessels. Pressure vessels are classified based on 6 criteria. First is based on wall thickness, thin wall vessel, thick wall vessel. Based on geometric shapes, cylindrical vessels, spherical vessels, rectangular vessels, combined vessels. Based on installation methods, vertical vessels, horizontal vessels. Based on operating temperature, low temperature vessels, that is temperature less than equal to -20 degrees Celsius. Second, normal temperature vessels, temperature between -20 degrees Celsius to 150 degrees Celsius. Third, medium temperature vessels, temperature between 150 degrees Celsius to 450 degrees Celsius. Fourth, high temperature vessels, temperature more than equal to 450 degrees Celsius. Next criteria is based on design pressure. First is low pressure vessel, that is pressure, operating pressure is between 0.1 megapascal to 1.6 megapascal. Medium pressure vessel 1.6 megapascal to 10 megapascal. High pressure vessels 10 megapascal to 100 megapascal. Ultra high pressure vessels more than 100 megapascal. Based on technological processes, reaction vessel, heat exchanger vessel, separation vessel, storage container. Now we will see the difference between thin pressure vessel and thick pressure vessel. There are three criteria. First is thickness. When the thickness is in between 1/10 to 1/15 of the inside diameter, it is known as thin pressure vessel. When the thickness is greater than 1/10 to 1/15 of internal diameter, it is known as thick pressure vessel. Second criteria is internal fluid pressure. If internal fluid pressure is less than 1/6 of the allowable stress, it is known as thin pressure vessel. If internal pressure is greater than 1/6 of the allowable stress, it is known as thick pressure vessel. Third criteria is application. Thin pressure vessels are used in boilers, tanks and pipes, whereas thick pressure vessels are used in high pressure cylinders, tanks and gun barrels. Stresses in a thin cylindrical shell due to an internal pressure. The analysis of stresses induced in a thin cylindrical shell are made on the following assumptions. First, the effect of curvature of the cylinder wall is neglected. Second, the tensile stresses are uniformly distributed over the section of the walls. Third, the effect of the restraining action of the heads at the end of the pressure vessel is neglected. When a thin cylindrical shell is subjected to an internal pressure, it is likely to fail in the following two ways. It may fail along the longitudinal section, circumferentially splitting the cylinder into two troughs. Second, it may fail across the transverse section, splitting the cylinder into two cylindrical shells. Thus, the wall of a cylindrical shell subjected to an internal pressure has to withstand tensile stresses of the following two types. First, circumferential or hoop stress, and second, longitudinal stress. Now we will see circumferential or hoop stress. In case of thin pressure vessel, while deriving the equation for circumferential or hoop stress, pressure P is acting along the x-axis. Therefore, consider a thin cylindrical shell subjected to an internal pressure P. It is having diameter d, that is inside diameter, and thickness t, and this L is nothing but length of the pressure vessel. Now, due to this pressure acting along the longitudinal, therefore pressure vessel will split into two troughs. This is one and this is second. Let P is equal to internal pressure, D internal diameter of the cylindrical shell, L length of the cylindrical shell, T thickness of the cylindrical shell, and sigma T1 circumferential or hoop stress for the material of the cylindrical shell. Therefore, total force acting on longitudinal section is equal to intensity of pressure into projected area, therefore is equal to P into D into L, that is equation 1. Therefore, total resisting force acting on the cylinder walls for two sections is equal to sigma T1 into 2T into L. By equating equations 1 and 2, we will get sigma T1 equal to PD upon 2T. Now we will see longitudinal stress. In case of longitudinal stress, pressure P is acting along y axis, that is along vertical axis. Therefore, because of that, this cylinder will split into two cylinders. Now we will see the derivation of its equation. Let sigma T2 is equal to longitudinal stress. Therefore, total force existing on the transverse section is equal to intensity of pressure into cross sectional area is equal to P into pi by 4 d square. Therefore, total resisting force is equal to sigma T2 into pi dt. Equating equations 1 and 2, we are getting sigma T2 is equal to PD upon 4T. Now we will see thin spherical shells subjected to an internal pressure. This is now spherical shell. This is thickness T. It is subjected to an internal pressure P. Therefore, let V is equal to storage capacity of the shell, P is equal to intensity of internal pressure, D is equal to diameter of the shell, T is equal to thickness of the shell, and sigma T is equal to permissible tensile stress for the shell material. In designing three spherical shells, we have to determine the diameter of the shell and the thickness of the shell. We know that the storage capacity of the shell is given by P is equal to 4 by 3 pi RB. Therefore, V is equal to 4 by 3 pi into D divided by 2 bracket cube. That is, V is equal to pi by 6 D cube. Therefore, D is equal to 6V divided by 5 bracket is 1 by 3. As a result of the internal pressure, the shell is likely to rupture along the center of the sphere. Therefore, force tending to rupture the shell along the center of the sphere or bursting force is equal to pressure into area, that is P into pi by 4 d square, equation 1. Also, the resisting force of the shell is equal to stress into resisting area, that is sigma T into pi dt. Therefore, equating equation 1 and 2, we are getting sigma T is equal to PD upon 4. Thank you very much.